In this video, we're going to talk about applying our logic to our programs. We're going to see if the study of formal logic has anything to say about our programs, the things that we write every day. We've seen how it can apply to English statements, English arguments, and even mathematics. But now, let's see if it can hit even closer to home and see if we can come up with a theory of program correctness. We need to understand even what we're talking about. When we say a theory here, this is a mathematical framework in which we can say precise things about program correctness. That's what we mean in this business when we talk about a theory. We don't mean, oh my goodness, some thing that may have occurred or might happen at some future point in time. We mean a framework that is mathematical in nature that allows us to say precise things. These rules of inference and associated axioms that we've been discussing so far provide that framework. So when we talk about a theory of program correctness, what we need to nail down are the correct rules of inference that need to be used in order to use formal logic methods to say important things and precise things about programs themselves. This is going to be the form of the formulas in the framework that we're going to use to logically say things about programs. The way you interpret this is by saying that this P here, this is the state of the system before our program runs. S is our program, and then Q is the state of the system after our program has completed. So what we'll do is we'll be basically given this P and Q and given a program, and it is going to be our task to say that, okay, we'll start with this material here that happens before the program is run, and then we'll run through the statements of the program, and then we'll see what the end result is. And if we can say that this whole thing is true here, it implies that S is correct with respect to that precondition and the postcondition. So when we say a program is correct, it's going to be in a very particular way, and it's going to mean that there's a precondition, there's a existing state of the system, and then there's a postcondition, there is a resulting state of the system, and in between these conditions lies our program. And the program is correct if it gives us the correct result for the proper input. All of this is important. You can't talk about what program correctness means until you nail down all of these. At least you can't talk about what it means in a formal sense. Of course we can talk about what it means in an informal sense. We can talk all day about what might be correct, or is that more correct than others. We might talk about style of the code as part of whether or not it's correct. But here, formally, we have to be much, much more precise about that. Hopefully, one of the things that you're getting from all of this work that you're doing is the difference between an informal knowledge of something and a formal, precision-based argument about something. And they're very different things. They each have their place. But when we're talking here about this theory of program correctness, and we want to prove that a program is correct, this is what we mean. And the big takeaway from this here is that you understand this as a case study. You see that this is an example of how we can apply our logic to a particularly important system. Start off with the assignment axiom. This is one of the first rules of inference that we require. We basically say that if we have at the beginning the fact that I'm going to replace t with x, x with t, and then I have my program statement that says x equals t, then at the end it's still going to be fine. So basically here I'm going to say I've got x equals 4 as my precondition, and then x equals x minus 1 is going to be my program statement, and at the end I get x equals 3 because I've replaced this 4 here in this formula and I end up with 3. This is a lot about like what we did with equality, where we went way beyond what an informal person would need to state about the properties of equality, and we do that for formal reasoning purposes so that we can say something very, very precise in a formal way. If x is less than 4 and you subtract 1, then now x is less than 3. These things are proven based on this axiom here, where basically we just replace, right? So I'm going to be able to replace this assignment with x in the precondition and then do math on it and get my postcondition. And this is basically the stand-in for that equality axiom that we were discussing previously. There's also a consequence rule. This tells us that if I have that P implies R, and then I have a program that runs from R as the precondition, I'm going to have the same result if I have that program running from P as the precondition. So P implies R. R runs the program that gives me Q, so I can start the program with P and end up with Q just the same. Because if I start with P, I'm going to end up with R, and then the program's going to give me Q. Similarly, on the other side, if I start with P and I end up with T and T implies Q, then it's the same thing as saying I start with P and I end up with Q. So here's an example. So let's look at an actual proof in this framework. Let's prove the correctness of, if I'm going to start with x less than 3, my program, it's one line, it's a great program, one of the best you've ever seen. It says x equals x minus 1. And then at the end, I want to prove that I'm still less than 3. So here we go. This is the assignment axiom. I'm going to start off with this value over here, and then I end up with 3. And then x is less than 3, so this is going to be my premise for this implication that I want. And then I get x less than 4. And again, we're going to use this t here because when we're working in the world of mathematics, we need to like add 1 to something or subtract 2 from something. And this t is just a stand-in for calling upon a theorem that allows us to do that. So if x is less than 3, then x is less than 4, right? Where's our rule of inference? Remember, every single thing that we have here has to be a rule of inference or it has to be a theorem. And so we're just going to say it's a theorem. It's a little bit beyond the scope of this course to get into number theory and set theory to the extent necessary to, say, prove this formally in those domains. So we'll just allow our intuition to carry the day here and allow us to say if x is less than 3, then x is less than 4. And we're only allowing that in the numeric domain. So we just call upon a theorem. So now I get x less than 3 implies x less than 4 with my consequence rule. And I end up with the thing that I wanted to prove. So two things. You should be thinking two things right now. You should be thinking, wow, that is the coolest thing ever, because I just used all this formal logic to prove something about a program, right? I took the applied engineering software development work that I loved, and I took this formal logic that I also love, right? You love it, right? Come on. It's well, whatever you feel about it, you take that on the other hand and you meld them and you get them together and you're applying it to a program. And that's awesome. However, what kind of program is it? It's like the worst possible program you could ever think to write. This is a silly statement. This is like back in geometry class in high school when you said, oh, this is a right angle, prove it's 90 degrees, and it was like 2 steps from the theorem, from the definition or something. It's like why would I even do this? This is just a case study. This is a proof of concept. And this whole section here is a proof of concept. This whole video is about this because really at the end of the day, if we have a program of any significance, we're not going to be doing this by hand. If we can even do it at all, we will be writing programs to do this. Remember, this is computation. And one of the big takeaways is that we can indeed write programs to run through these proofs for us. And if we're proving something about a program, now we're in the world where we're writing a program to tell us something precise about another program. Right? All right. Let's do another example. So now here we have there exists a y equals 2x. So if there exists an x such that y equals 2x, so basically if y is even, right? We've seen that definition. And then I add 3 to y. Now y is odd. That's what we're saying here. We start off with an even number, you add 3, you have an odd number. That's what this is proving. And this is my one step of my program. So we start off with this rule here, with the assignment axiom. I'm going to be able to just represent the y plus 3 here. I can just take this and just put it in for the y there. That's how the assignment works. And then I'm going to introduce a new premise because that's how CP works. You introduce a new premise and now we're in a subproof. Y equals 2c. because this is existential instantiation. We're in an existential here. We say that there exists an x such that y equals 2x. So okay, let's name it. We're going to call it C. And now we're going to take this and we're going to see by our equality rule that we can just represent it thusly. And then modus ponens allows us to conclude that this second part over here is true, because we have the first part and then we get the second part. So good old modus ponens. No matter how wild we get, no matter what sort of rules of inference we develop, no matter what sort of application domain we're in, we still have modus ponens. It's our good friend. It gives us comfort at night. It gives us comfort in the storm. Now we can add 1. We can basically break this up. We're factoring, right? 2c plus 3 is 2 times c plus 1 plus 1. This is just arithmetic, so we'll just say it's a theorem, right? This is just arithmetic. And again, if we are in number theory, if this were a number theory course, this would be a significant result. So just go take that class and then come back, and then you can fill in the details for this theorem. Now there exists an x such that this thing is true, which is kind of what I wanted up there. Existential generalization. I can now go back up this way. I had to put it in this form in order for EG to work. And then I've gone from 2 to 7. I've proven my CP, and I can pull out now and have this result, which allows me, with the consequence rule, to end up with what it was that we were trying to prove. Again, we're not going to spend enough time on this for it really to be worth our while to become super experts at proving programs correct. That's not the goal here. It was the goal to become super experts at understanding the propositional and the predicate calculus. Those things were super important. But this is just it's a one day just looking at a particular application. So I'm not going to tell you to study in detail every single line and be able to be expert at every single jump in reasoning that occurs in this video. What I want you to take away from this is that it's just a particular application, that this is something that we can do with our formal logic. We can take basically any domain out there that you want to say something precise about and come up with some new rules of inference and then run through proofs like this. And this is now formal reasoning. Composition rule says that if I start with P and I run a program and I get Q, and then I start with Q and run a second program and I get R, then I can start with P, run both programs in succession, and get R. And this is a great example too, right? This seems obvious, right? But it's not in our system, right? We have to add it to our system. The fact that it seems obvious makes it a wonderful case study in what we should add to our system, right? It's justifiable to add this to our system because it seems obvious, but it has to work in that direction, right? We've got to add them and then see what sort of system that we get, see what the mathematics says afterwards. And then generally the way these systems work is that the inclusion or exclusion of particular rules of inference are justified based on the results, based on the beauty of the mathematics that arises from them. So we'll do this again. We start off with this assignment axiom twice, then we can finally use our composition rule. We put both of these statements together now in the composition rule, and we're building up something that is of that form, and now we come up with this premise here, and we run through. If x is less than 2, then 2x is less than 4. We just need that to build up our goal statement here. So again, we're referencing some theorem of arithmetic that allows us to double both sides of an inequality. Then again, we can, what are we doing? Subtracting 3 from both sides of the inequality. We've done this before. We're fine with that. We pull out and we've got this. Now it's CP, and with the consequence rule again, we end up proving what we set out to prove. If then, so basically what we're doing is we're going through all of the different types of statements that we have in our programs, and we are analyzing them in terms of a rule of inference. We're taking the structure of our problem domain and translating every element of that structure into a proof rule. And that's what I want you to get out of this. I want you to understand that process. I don't want you to have to fight through all of these things. I'm not going to ask you to use the if-then rule in an assignment. The assignment associated with this video is going to be incredibly straightforward. It's going to be just from the beginning part. This is much more about being able to see that we can indeed apply our formal logic to something beyond what we've seen before. So we can talk a little bit about this. What we're doing is we've got this statement here: if x is greater than 1, then x is going to be decremented. And so if you start with x greater than 0 and run that program, then you're going to end up with x greater than 0, right? This is a great thing, right? But humanity is now advanced because we've proven that this is true. So we can run through this. So you start off with your assignment axiom, then you have to come into your CP proof in order to show this part, and then we can use the consequence rule and then run back into a second proof and use CP again, and then finally we apply our if-then rule because we've set up here. So you might wonder, how do I know what the premise should be here? How do I know what I'm targeting in my proof? And the answer to that is you're targeting whatever the proof rule is that you're trying to use. And we've said from the outset in this particular example that we're using the if-then rule. So it makes sense to run through it. This is like in your calculus class where you knew what form of integral it was, right? You knew that you could use trig substitution, or you knew that you could use integration by parts on a particular problem, and that made it a lot easier. So that's kind of what we're looking at here. Okay, there's just going to be one more of these, just one more. We're going to look at a while statement. So if I have P and C true, and then I end up with P at the end, then while C do S, P and not C. So we'll start off with P. We're going to run through this until C is false, and then you end up with not C at the end. So if we've got this while loop that depends on C being true, when we exit our program, we now know that C is not true anymore. And this is really the main takeaway. This is the cool part here. Not so much the proof that comes after. Don't get too buried in the proof. That starts to hurt your head. Just say, hey, it's almost July. I'm gonna go shoot off fireworks and not worry too much about this. But this statement itself is something that you should take with you. And because this is a formalization of the while statement in our programming languages. If we want to understand programming better, one of the great ways to do that is through this sort of formal precision. We can understand what while is doing as a programming construct by translating it in this way into our formal system. P is a loop invariant because it's true both before and after the loop. It hasn't changed by the loop, but C changes because my loop depends on C as its condition. So here's something to try to prove. We want to prove that if I start off with an integer that's greater than 0, and then I run something, I divide it by 2 while that integer is even, I end up with an integer that's greater than 0 and that's odd. So we're just going to keep dividing by 2 while it's even, and this is integer division, so it ends up with an odd number at the end. And this is going to match the conclusion, and the reason it's written this way is because of how this is all structured. C is going to be even, so we start off with an even number. So we have to show something of this form, right? So one of the things that we have to do is map the kinds of structures that occur in our systems to the sentences in our formal logic. So the reason that we are sort of contorting ourselves to do that in this case is because of where we're at, of the fact that this rule has this particular form. So let's look at the steps of this. We start off with our AA. We're generally always doing this. We were coming up with some sort of statement here about this, and then we have our original statement and even, and then we can simplify, we can apply some rules to this from arithmetic, and we run down. We know that if we have an even integer, then x over 2 is even. This is just, again, from number theory, just from how numbers work. There's a theorem here, and we end up being able to prove that what we wanted to prove is true. So I know we did a bunch of these proofs. We went through them, and it's pretty quick, and this is going to be at the edge of your comfort level, the edge of your understanding. In this particular video, you're probably a little bit more cloudy about what's going on. So just to recap, what we've done here is we have a particular problem domain that is of interest to us, and we are specializing our formal logic to deal with it, to say precise things. And the way we specialize our formal logic is by looking at the constructs in the programming languages that we care about, our if-else statement, our assignment statements, our while loops, and formalizing those sorts of things. And this is how formal logic can inform how we look at and how we say formal things about particular systems. I'll just say it, that this section is nowhere near the most important section in this course, but it's just another example of the applications of what we've been spending time on with the propositional and the predicate calculus.